In a groundbreaking astronomical discovery, scientists detect ghost particle neutrinos from the middle of the Milky Way. Neutrinos are one of the lightest elementary particles in the standard model of physics. Due to their weak interaction with matter, it's been elusive for a long time. This remarkable discovery marks the first time astronomers have been able to create a new map of our galaxy. Rather than through traditional observation, but by capturing these elusive examples of matter. As our understanding of the Milky Way expands from gamma rays to radio waves, this new path to characterize the Milky Way with mesoviolet light adds a previously unseen dimension to our view of the universe. So how did astronomers find that these examples really came from the center of our galaxy? Why are neutrinos called nature's ghost particles? Last but not least, what does the discovery of neutrinos from the center of the Milky Way mean for astronomers? In the vast ballet of cosmic particles, one particle is very striking. That's the neutrino, often referred to as ghost particles. These basic examples belong to the class Neutrinaceae. That means they have a half-integral option and are themselves inseparable. There are three types of neutrinos: electron neutrinos, tau neutrinos, and wood neutrinos. Each is connected to the corresponding basic examples of electronic No and iron. Although neutrinos are not the building blocks of other matter, but they have huge significance in the cosmic game. The special properties of neutrinos distinguish them from other fundamental examples. First of all, they're electrically neutral. This means that even the strongest magnets cannot detect their presence. Secondly, their quality is almost negligible. This makes it difficult for them to interact with regular substances. They travel directly through the star at nearly the speed of light, planets, and even our bodies. About 100 billion neutrinos pass through every square centimeter of your body every second. That means trillions of neutrinos pass by every second. And we don't even notice. This ability has earned them the name of a nation of ghost examples. Although their existence is subtle, but neutrinos play a crucial role in our quest to understand the complexity of the universe. And you wonder what the origin of this is? Well, mesomicrots are produced in a variety of nuclear reactions, both natural and artificial. The most common phenomenon leading to the creation of neutrinos is a high-energy reaction involving protons and atomic nuclei. This reaction can be carried out in a nuclear reactor, man-made in nuclear bombs or particle accelerators. At the forefront of astrophysics, neutrinos can arise naturally from nuclear reactions. Happens in the core of a star. An interesting fact is, Most neutrinos detected on Earth come from the Sun. Internal nuclear reactions result in the equivalent of about 65 billion solar neutrinos per square centimeter per second on the Earth's surface. In addition to these sources, neutrinos also happen in supernova events. However, a recent study highlights the formation mechanism of neutrinos and cosmic rays. These cosmic rays are high-energy particles from various sources in space, and when they interact with atoms, they produce neutrinos. For years, researchers have believed that high-energy neutrinos only come from stars outside the Milky Way. However, astronomers have long suspected our own galaxy. The Milky Way could be the source of such neutrinos. When cosmic rays collide with dust and gas in interstellar space, an interesting process that generates gamma rays and high-energy neutrinos occurs in our galaxy. Let's take a closer look at how this fascinating phenomenon unfolds. When cosmic rays interact with interstellar rings, they produce an example of instability called a ring. A meson is made up of a quark and an antiquark. There are three types: positive, negative, and neutral. Charged rings have a relatively short lifespan before aging, about 26.33 seconds. On the other hand, neutral mesons have a shorter lifespan, approximately 85 seconds. When a neutral meson undergoes decay, they emit gamma rays. The disintegration of charged mesons produces high-energy electron neutrinos. Previous studies have successfully detected gamma rays from the galactic plane. This led scientists to predict the existence of high-energy neutrinos in that region as well. However, as mentioned earlier, neutrinos interact very weakly with matter. This makes detecting them an extremely challenging task. However, despite the intricacies, but for researchers, detecting and studying these elusive ghost particles is not an impossible feat. And the way it's done at the South Pole of Earth will surprise you. Detecting high-energy neutrinos on Earth requires meticulous precision and great patience. In this effort, facilities like DingCube play a crucial role. Soldier Cube at Scott South Pole Station in Amundsen, Antarctica is a giant probe. It's made up of 5,000 optical sensors, hanging from 86 ropes. These strings drill holes deep into the Antarctic ice. The hole can be as deep as an impressive 1.56 centimeters. Most neutrinos pass through the Earth without any disturbance. Occasionally, they interact with water molecules. The ring produced by this interaction appears as a flash of light within the detector's sensor. By analyzing the patterns of these flashes, researchers can rebuild energy. In some cases, it is even possible to determine the source of the detected neutrinos. However, pinpointing the source of neutrinos much depends on a clear path for the detector to record the initial direction of neutrinos. Although some neutrinos exhibit well-defined trajectories, but other neutrinos can produce complex optomechanical curtains, generate fuzzy hairballs, blurring their origin. Therefore, detecting and determining its source may require extensive observations. In this groundbreaking study, researchers harnessed the power of machine learning to analyze 60,000 multiple detected microstimuli collected over a decade. By feeding this massive dataset into their algorithm, they generated a fascinating map, revealing the origin of neutrinos scattered throughout our galaxy. As research theory, this graph in the text shows, in the map of Zhejiang, the plane of the galaxy is represented by a gray curve. The center of the galaxy is marked with a dot. The darkest dots on the map show the areas with the worst emissions gluts. When comparing this neutrino map to a map of optics and gamma-ray frequencies, a startling observation emerged. Neutrinos overwhelmingly come from regions where high gamma-ray techniques have previously been detected. To get this neutrino map, researchers carefully filter out background neutrinos, especially borrowed from neutrinos. They come from interactions in Earth's atmosphere that can significantly interfere with astrophysical neutrino detection. Unique straight-line trajectories produced by MIU neutrinos make it easy to reconstruct historical directions. This is a key aspect of neutrino astronomy. The team's innovative application of machine learning technology enabled them to include 20 times more event-enhancing directional information in the data. Ultimately, more accurate and precise results were obtained than previous studies. According to statistics, the neutrino flux observed at the center of the galaxy exceeds the background noise by about 4.5 times, represents a significant 4.5 sigma assay. Although he falls slightly short of the traditional Wu sigma high intellectual trust path, but the neutrino surplus observed from the galactic surface provides convincing evidence, prove that the Milky Way is the source of high-energy neutrinos. Considering that the study of celestial phenomena relies mainly on photons for observation, this discovery is a significant breakthrough. Now, with neutrinos being used as a tool to map the universe, we stand on the threshold of an exciting future. By exploiting examples that were once almost undetectable, we have a new understanding of the universe. He turned on exciting. The possibility of perceiving reality in a whole new way extends our ability to explore the mysteries of the universe. A recent study using data from James Webb revealed that the age of the universe could be 26.70 billion years, almost twice the current accepted age. If you missed this episode, be sure to catch up on this interesting discovery.